Good morning. My name is Mike DeLacluse. I'm showing 9 o'clock, so we're going to go ahead and get started. I'm president of the Lesman Instrument Company, and I'd like to thank all of you for taking time out of your busy schedules to join us for today's webinar, an intro to ISA 100.11a wireless standard. It's presented by Honeywell's Brandon Gust. Today you're going to learn a little bit about the standard, how the ISA 100 is implemented and why, and some of the differences between the ISA standard and WirelessHART. Brandon is currently Honeywell's Field Products Wireless Specialist. For the past 6 years, which is almost as long as the standards have been around, Brandon has been with the Honeywell Process Systems Wireless Group and a Field Products Wireless Consultant. Prior to that, Brandon has 20 years of networking experience and is a Cisco certified network professional. So I think Brandon's been around wireless for quite a while. With that, I'm going to turn it over to Brandon and let him give our presentation.
Okay. Thank you. Good morning, everyone. There we go. Okay, now we're good. Okay, what we're going to talk about this morning is I'm going to start off by introducing what the ISA 100.11a Industrial Wireless Standard, what it is, why it came about, what the benefits of it are. Then we're going to roll into the topologies, the Honeywell implementation of the standard, and then we're going to talk a little bit about competitively comparing the ISA standard to the WirelessHART standard to kind of give a to kind of draw a differentiator between the two. So, what is the ISA 100.11a standard? The idea was to come together and create a wireless standard for non-critical monitoring, alerting, and control applications. And they clearly defined the protocol suite, the management system, or the system management rather, the gateway, and a laundry list of security details. I'm not going to go into security in great detail in this presentation. I will touch on it. Suffice it to say, it is they spent a lot of time building in security mechanisms for this standard. It's intended for low data rate wireless connectivity with fixed, portable, and moving devices to support limited power consumptions. The idea here on these transmitters is for them to be battery powered. So that was another key to creating the standard, is creating something that didn't use a lot of batteries, so the batteries could stay alive for much longer. And low data rate, it kind of touches on the fact that the amount of data being transferred from the process to the DCS isn't a great deal of data. So by allowing for that in the standard, the scalability is much higher as well. So it addresses the performance needs and needs of applications for monitoring and control, where latencies on the order of 100 milliseconds can be tolerated. I'm going to talk about latency as we go forward as well, because that's going forward. That's a latency. What latency is the time it takes from the time the data leaves the transmitter in the field to the time it's displayed at the DCS. So that's as it relates to control, latency is a very big deal. The fundamentals of the standard are these. It's an open communications protocol, meaning that anyone can manufacture to it. It's not locked down. Honeywell doesn't own it. No one owns it. The ISA dictates to us how we what we have to manufacture to. The third bullet there is important to me because, as Mike said, my background is Cisco networking. That's the OSI 7-layer model. When I saw that they used that as their design basis, that was a good thing to me, because that's what gave us IP. If you think back to, I'll use an analogy to the wired networking world. If you think back to the mid-90s, everyone sort of lived on an island in the networking world. Novell had IPX, Apple had AppleTalk, Digital Equipment had DECnet, Microsoft had was doing their thing. Everyone sort of lived on an island. The IEEE got together and said, if this whole internet thing is ever going to be anything, and business networking is going to go forward, we need to all get on the same page. So that's where IP came from, and they used the OSI 7-layer model. It's open system interconnection is what OSI means, and all it does is in 7 layers clearly define everything you have to do to meet the standard. And that's the model that the ISA chose to use. So that's what makes the ISA easily manufactured to by other people other than just who created the standard. It does use the IEEE 802.15.4 radio standard at the physical layer. That does live in the 2.4 gigahertz frequency band. They did that for global unlicensed deployment. So there are factors to keep in mind because of that, but that's why they use the 2.4 frequency band. It uses an algorithm to determine best link formation. What that means is as these devices come up and power on, there's an algorithm that runs in the background that always wants the cleanest, most efficient way to get that data out of the process and into the DCS to be displayed. So we use over-the-air firmware upgrade, configuration, and provisioning tools. What that means is once the transmitter is installed in the field, you're not going back to it to do anything except once every 3 to 5 years to change batteries. All of the configuration, all of the security, all of the firmware, everything is done over the air. Oh, I apologize. One thing I meant to say, due to this format, if we can kind of make notes of questions, and then at the end we'll have a Q&A. That way we can move through this in kind of a timely fashion, and then we'll have a Q&A that can run as long as we need to at the end. Benefits of implementing with the ISA: predictable and interoperable performance. Obviously, that's due to the fact that it's an open communication standard that multiple vendors can manufacture to, and we can all play on the same field. Flexible and deterministic operation. Deterministic operation is the algorithm that I described in the previous slide. It means the algorithm always wants to find the most efficient way to get that data out of the process into the DCS. Reliable and secure data transmission. Everything to do with the industrial world centers around reliability and security. We have to know that that data is going to be there when we want it, and we have to know that that data is being transmitted securely. There are several mechanisms built into the standard to ensure that, and we'll discuss that in the next couple of slides. The ISA chose to support routing and non-routing devices. What that means, this is a very important topic to understand. What that means is if I need to, or if the situation calls for it, these transmitters can be turned into routers as well as transmitters. I don't want to do that. As a design, when I'm designing a wireless network, I want to design it properly on the front end. I don't want to have to go back and turn on routing and transmitters to make up for a design problem. Where that comes in handy, and I'll touch on it a few more times as we go forward, because in my opinion, it's kind of a big deal. What that gives us is the flexibility to solve problems. If you have an outlying transmitter, for example, that can't see back into the network, to the mesh, then you turn on transmitters that are closer to that problem transmitter, and now it has a way back in. We didn't need to extend the network to catch one transmitter. We have ways to overcome those problems like that. But at the beginning, on the front end of the project, I don't want to have device routing in mind. I want to build it out properly in the first place. Characteristics of the standard. The data reliability mechanisms that are built in, it is a frequency hopping mechanism, time diversity, and determinism. What time diversity, we talked about what determinism is. What time diversity is, it relates to, if you kind of look down on the power usage section for precise transmit receive time slots, that ties to time diversity as well in the reliability talk. Every transmitter is given a specific time slot to transmit in. That the wireless device manager is kind of what we call the gateway or the server in this situation. Determines it dictates that every transmitter's time slot. It tells it at time of boot up, you're to broadcast here, and that's the only time it broadcasts. So as that frequency hopping pattern rolls around, that transmitter knows when to broadcast. It comes on, broadcasts its data, and then stops broadcasting its data. So that allows for the reliability portion of that is this, that the wireless device manager knows it was expecting that particular transmitter at that particular time. If it doesn't get it, it goes out and asks for it. So there's that's the reliability portion of that. Collision avoidance. Wireless is a shared medium, meaning the air is the air. Whatever RF device is powered up, you're all sharing the same space. So what this system does is it has what's called clear channel assessment. When it boots up for the first time, it more or less sniffs the air, decides what's out there, if anything, and it goes to a part of the frequency band that's least congested. If it sees something at the top of the band, it'll choose to operate at the bottom of the band, so as not to cause interference or be interfered with. That third bullet, antenna diversity, is a nice feature as well. What antenna diversity is when we get to the product itself, you'll notice that there's two antennas on it. This is a mitigation process for what's called multipathing. Multipathing is a wireless phenomenon that a RF signal bounces off of metal, and as it bounces off of metal, it becomes corrupted, it gets out of phase, it causes problems. Antenna diversity is the mechanism that mitigates those problems and allows us to operate much more cleanly in a highly industrial environment with a lot of metal, a lot of piping, I-beams, things like that. The data security mechanisms that are built into this protocol, it uses 128 block AES ciphers. That's industry best for encryption. Message authenticity checks. There is a back and forth on every message that's sent to ensure that the correct device is who sent that message. And flexible security key distribution methods. There is a manual intervention, a human intervention to allow every single device onto this network. There is no automated process. There is no way to circumvent that. In an existing system that adds new devices, a person has to physically be in front of the interface, see them join, and then allow them to authenticate to the network. Like I said, there's no way to automate that process. That would be a security problem. And then power usage. I mentioned that these transmitters run on batteries. We talked about the precise transmit and receive time slots. Where that relates to power usage is here. That transmitter isn't just broadcasting constantly. That would kill the batteries. It broadcasts its data at the exact time it was told to. Then that radio, the only thing the radio does in the meantime, and the rest of the time, is a beacon or a RF keep alive to maintain the link. So that allows us to get much more life out of our batteries. And non-routing nodes, the minute I turn routing on a transmitter, it destroys the battery life. So I mentioned I don't want to do that, and that's one of the main reasons why. Adjustable power levels for the radios. What that means is I have the ability with these radios to turn the power up and down depending on the situation. So if I have a highly congested situation where the radios are close to each other, the noise level's high, so the batteries are getting used up a lot, I can turn that power down, thereby lowering that noise level in that area and saving the batteries. And last but not least, these transmitters use standard off-the-shelf lithium thionyl chloride batteries. The ISA chose not to make customers beholden to any one manufacturer for a battery pack. You can source these batteries. If you Google it, you find them. They're pretty inexpensive. So the number one differentiator and the number one thing, in my opinion, as a network guy, that the ISA chose to do is utilize a backbone type architecture. And this is what I like to refer to as proper networking, or best practices networking. Back in the 90s, when I first became a network engineer, we had tokenry. We had peer-to-peer networking. That was not uncommon at all. We quickly realized that was not the correct way to do it. As speed started growing, data started getting bigger and bigger and bigger, things like that, and sharing became much more important. We realized that a distributed backbone architecture was the way to go. So now, in everybody's office, everywhere you connect to a network, there's a cable that runs back to a switch that connects up through a network. You don't have a cable that runs from computer to computer, or you don't have a wireless system where a laptop talks to a neighboring laptop and so on and so forth around until it finally gets to where it's going. That's the architecture that the ISA chose to implement in this as well. And it looks kind of like this. But what you see there is a picture of what we call an FDAP, or a field device access point. That is the powered architecture device. Think of it as an access point just like you would think of a Cisco access point in your building. Except this access point is for field instruments only. They talk to each other. At a minimum, one has to be wired. Even though it's wireless, there's still got to be a way to get back on the network or to the wire. At least one of them has to be wired. Then they form a mesh amongst themselves, and the transmitters then talk up to the mesh as clients, as a client would talk up to a enterprise network. Ultimately, getting back to what we call the wireless device manager, or the WDM, it's the controller for everything wireless. It's the brains of the operation. There is no function of gateway in a radio. All of the gateway functionality, all of the control functionality is built into the wireless device manager. It is it's a DCS appliance meant to be rack mounted, so it's protected. If we do end up needing to use wireless field instrument routing, this is kind of a graphic of what it would look like. I can hop through transmitters to get back to the mesh. A couple of implementation examples. The top one would be a single wired FDAP, kind of a base system with no redundancy, meaning this is kind of the simple starter kit idea way to do things. You have one wireless device manager, you have one FDAP that's connected to the network, and then all of your transmitters then have one single path created up through that field device access point onto the Ethernet segment back to the wireless device manager. Now the bottom one shows a more redundant setup where you have two wireless device managers because they can sit side by side in kind of a hot standby situation. Or if one fails, there's an automatic failover and there's no data loss. Then you have two wired FDAPs, so you've eliminated that single point of failure as well. And the algorithm recognizes, if you look at the top example, the transmitters only have one path because there's only one FDAP. If there was a non-wired FDAP in that example, they would still only have one path. The algorithm recognizes that there's a single point of failure at the wireless side where it connects to the wire, and it will not allow the transmitters to form up redundant paths because there is a single point of failure in the network. That's a software feature they built in to try to ensure that we always design in redundancy. So the bottom one would be what it should look like. And with the little example off to the left there of transmitter routing, where all of the transmitters have two paths, all of the field device access points have two paths, so nowhere in the network do you have a single point of failure. Actually, I want to go back to that slide. There's a topic that I think this is a good place to make. It's, in my opinion, the second most important feature of the system behind the backbone architecture, and it is this. It's the way that we form dual paths. And I'm going to explain how it's different. Everyone in industrial wireless forms two paths. That's a critical piece of the puzzle. Everyone does it. Everybody recognizes that that's absolutely necessary. But what the ISA chose to do was make it a little different. We have what's called duocasting. And what duocasting means is every device that you see in that example that has two paths is sending its data out both of those paths at the same time. Meaning they're in dual path formation, it doesn't form in the sense of a primary and a secondary where there has to be a failover in the event of a failure. In the event of a failure in this system, the data was already flowing another path anyway, so there is no failover. It just continues to flow as normal. Everything's good, and then the devices that experience the failure go out and start trying to reestablish another path while still sending the data out the path they already had. So if in this situation, if that lower middle FDAP fails, none of the data from those transmitters is ever going to experience a disruption at the DCS side. It's just going to keep flowing. Everybody's going to recognize that they had a failure, and they're going to start forming around that failure. These are the ISA compliant devices. The system consists of 3 different devices. We talked about the wireless device manager, the WDM, the field device access point, and the XY6000 field instrumentation. The wireless device manager. It is the, like I said, the brains of the operation. It manages the field instruments and the network devices. It's the gateway between the wireless world and the wired world. It's the security manager. It controls everything to do with the wireless side, meaning everybody that's allowed to join, and then obviously who's not allowed to join as well. It serves as the interfaces available out of that are Modbus, HART, OPC, UADA, CDA, and a GCI tunnel. It has there is no software to this device at all. It has a web-based interface that allows you to control everything. You log in via an IP address, and it brings up. There's one page, extremely simple. All of the configuration and all of the administration is done through that web page. It is an integrated firewall. If you notice in the graphic, there's 3 Ethernet interfaces. The top 2 are the important. The bottom one, I'll start that way. The bottom one is the redundant interface. That's where a cable runs between 2 wireless device managers that are in redundant state. That's what controls the redundancy. The top 2, one of them faces the wireless side and one of them faces the process control side. That's a hard firewall. The only thing, there is no concept of traffic flow through that firewall. I'll use Modbus for example. The Modbus table is built in this wireless device manager. So the data is posted to the Modbus register by the attribute, and then when the DCS asks for a register number, the value is then provided to the DCS. There is no sense of a flow of the PV through the wireless device manager. It's a kind of a server situation when it comes to Modbus. The GCI tunnel is a little bit different story. They had to, what the ISA chose to do here is accommodate higher bandwidth protocols such as the NRAF Engage protocol, the GE Bentley Nevada vibration, full spectrum vibration solution. Those 2 examples use a much larger a chunk of bandwidth. So they built what they called a GCI tunnel through the frequency hopping mechanism. So it allows the transmitters, which operate at a much lower throughput, to coexist with these higher throughput protocols, and neither one disrupt each other. So I can get a full spectrum vibration analysis or the higher bandwidth level monitoring that the NRAF Engage protocol offers as well, all through this system. That's something that's unique to the system, by the way. And as I mentioned, they are fully redundant. They can be fully redundant. They can operate autonomously or in a redundant situation. This is what the interface looks like. Again, you browse, you use Internet Explorer, you browse to a IP address, log in, this is what comes up. The structure of this it works like this. Everything in the left-hand pane is everything that you have in your network. All of the field device access points and all of the transmitters. The middle is kind of an at-a-glance network help map. You can also import a map of the facility in that section and place those devices where they actually are, so you can see what transmitter is talking to what field device access point and how well it's talking. It gives you a list of network or wireless diagnostics, so you can see if a problem is coming or if there is a problem. And then there is a right-hand pane that's collapsed. If you look on the right-hand side of the interface, you see it says property panel. That's expandable just like the one on the left is. That is where all the configuration is done. So you would highlight the device, and then everything that you can do to that device then appears on that right-hand pane. You configure it, you apply it, it pushes the changes over the air, and you're done. You're not going to the device to do anything at all in the field. The field device access point is a field device. It's an access point for field instruments only, meaning it's not a Wi-Fi radio. There is no real or perceived security issue here because there is no laptop chipset. There's no app for that. There's nothing that can associate or even see this network when it's up and going, for that matter. It's a low-powered frequency hopping mechanism that a fixed channel wireless device like a laptop or a phone or something like that, it can't even see that it exists. We talked about what the dual antennas do and why they're there. We talked about what a self-healing, self-meshing network is. That means in the event of a failure, it heals around it in the background without any user intervention. There's roughly a 450-meter field of access, of data access from wireless instrument to field device access point with standard integral antennas. That's a line of sight distance. Keep that in mind, please, when we're talking about distances. That is strictly line of sight. Any obstructions you have in between shortens that distance. So it becomes situational on how far a transmitter can get back to a field device access point. The operating temperatures, -40 to plus 75 Celsius. I don't think you probably don't have to worry about that too much in the U.S. The power options directly correlate to the classification division rating of the device. You have an option there. It can either be Class 1 Div 1 or Class 1 Div 2. If, for whatever reason, and it's extremely rare, that it does have to be mounted in a Class 1 Div 1 environment, the only power option is going to be 24-volt DC. If it's Class 1 Div 2, the FDAP comes with the power supply inside the box. So you can power it either way, 24-volt or 110, 230. The dual antennas, we talked about that. Every FDAP in a network can support up to 60 field devices at 5 seconds or greater reporting rate. If that number, if your update rate requirement is 1 second system-wide, that number goes to 18 per FDAP. The system limitation, and I don't think that's in here, I'll talk about it real quick. The system limitation for transmitters, when I talk about system, I'm talking about the WDM, the Wireless Device Manager, controls the system. Each wireless device manager can handle 100 transmitters. It doesn't matter about the update rate. It can handle 100 1-second update rate or a mixture of update rates across the network. The scalability as it relates to number of devices is important at the field device access point level, and that's a throughput and a bandwidth issue. Is we have to make sure that we stay conservative and make sure that all of our 1-second update rate transmitters are going to get through when they're supposed to. The instrumentation. What does the transmitter do? It measures and wirelessly transmits data in industrial and hazardous environments. Configurable data routing, we talked about that. The data routing as well as the update rates are individually configurable per transmitter, meaning there's no concept of a zone or a group or an area. One is not dependent on the other. If I'm making one a router and it's at 10 seconds, it can route a 1-second update rate transmitter. It's not that it's at the functionality level, it's not a problem. Like I said, all of the firmware upgrades and all the configuration is done via the interface and pushed over the air to the transmitter. Once it's installed, I don't want to go back out and touch it for a while until I got to go change the batteries out. The suite of pressure transmitters are these. There's differential pressures that come in those flavors, gauge and absolute, as well as dual head and gauge pressure. So each one of those transmitters is a different part number. So there's a host of transmitters to meet the pressure needs. The temperature measurements, which are much more common, that transmitter is a 3-input transmitter, and the 3 channels are configurable in that host of ways. It can support up to 3 thermocouples, 3 digital inputs or discrete inputs, or 2 3-wire RTDs. So they can also be configured to be millivolt or HLAI channels as well. We also have just an HLAI transmitter, just a current input transmitter, and then the universal transmitters. The universal transmitters come in 2 flavors. If you notice the 3rd channel, they're 3-channel transmitters, but the 3rd channel on these universals are not configurable. On the 700, it's always an analog input, and on the 701, it's always a discrete output. So that 701 is our discrete output transmitter. So in the other 2 channels can be configured in those ways: millivolts, thermocouples, or analog inputs, discrete inputs. We have the OneWireless adapter. What the OneWireless adapter is It attaches to a wired HART device and encapsulates that HART data into ISA 100 wireless traffic, transmits it over the network. When it gets back to the wireless device manager, the wireless device manager then acts as the HART mux and distributes that data to the wire as if it was never anything but HART data. It's Class 1 Div 1. It's got roughly a 1,000-foot line-of-sight range, and it is powered from the same 4 to 20 loop that you're bringing that HART data from. And it has one D-cell battery just for the radio. It's the same batteries that the transmitter uses. It's that D-cell lithium battery. Some additional values: the flexibility for adding new I/O enables new measurement and control applications, and where wiring costs are prohibitive, and easy to relocate transmitters if the application changes. One that kind of relates to that, I'll use an example that's come up a couple of times recently at existing networks. The maintenance department, and this has happened at 3 different refineries around the country, the maintenance department kind of finds out the functionality of this network, and they're putting these transmitters on their shelf for troubleshooting purposes, meaning if they have to go install a transmitter, if they're having an issue, they don't have a reading where they need one, instead of installing a transmitter, running all the cable, running all the power, just to find out what the problem is, they have this wireless network already in place, so they put the wireless transmitter in, put it in, and then a fraction of the time, they're getting the data back into the DCS for historization and troubleshooting purposes. Then once the problem's found and solved, they either leave it there or they pull it out and put it back on the shelf for future use. So today's requirements for wireless implementation, it's kind of going, this is today and going forward. Redundancy is a very big deal. We talked about dual path communication and why it's important and how we do it a little bit differently. In redundant system manager and gateways, so it's redundant. There is no single point of failure throughout the entire network if it's built out to that fully redundant state. And then the expanded use of the 1-second update rate. We worked very hard to make the 1-second update rate system-wide while still maintaining an acceptable battery life. So while it's not the 4 to 5 years that we expect out of a normal battery, it's about maybe 2 to 3 years in good conditions. But that's still a pretty acceptable battery life out of a 1-second update rate transmitter. The control. We're talking about control over wireless going forward. It requires the ability to define latency. We talked about the latency is the time it takes the data to get from the transmitter back to the DCS. In order to go forward in even non-critical control applications, we have to be able to know how long, what that time is. That's where the backbone comes into play. That's where the backbone architecture comes into play. Because if I can clearly define that, because I have a stable, properly built-out network that's supporting those 1-second update rate transmitters or those control-based transmitters. So I know exactly how long it's going to take. I don't have to worry about it going from transmitter to transmitter to transmitter. That latency is all over the board. It's much, much longer, and you can't define it. It can take different amounts of time depending on the load on the network. And going forward with new solutions that weren't practical or possible before. Wireless vibration, I touched on that with the GE Bentley Nevada solution. There's SKF also makes a wireless vibration solution that's ISA compliant. Safety shower monitoring, that's an example of other divisions of Honeywell adopting the ISA standard. The sensing and control division has a limit switch that they're installing on safety showers that are showing, that are alarming when the safety shower is activated or eyewash station is activated. So they're getting precise alarms on exactly which shower was activated. Someone that implemented this, another refinery out in California that implemented this, got kind of an unintended benefit. Some state regulation came down on them that said they had to record, I guess, have a recorded test of their safety showers. I think they had to test them once a month. So this made it much easier. When the safety shower was activated, not only did it alarm, it also historized that event. So through the DCS, through the historizations they already had, they had a record that they were testing the safety showers and eyewash stations. So that was kind of a cool little thing that happened that wasn't a selling point of the system, but it happened on the back end, and they were pretty happy for it. And redundant level monitoring. Redundant level monitoring is a big deal now across the world, as far as I know. I mean, everybody's doing it. They're having to put in 2 independent tank level monitoring systems. The current one's wired. That's great. The wireless one provides not only a secondary measurement, but also a completely secondary or separate communication path. So you're getting more or less 2 levels of redundancy out of that second device. You're not wiring it, running it through the same cable tray, so in the event of a physical problem in that cable tray, you're not losing both level indicators. At the standard, the 2 wireless standards that are really out there now, and there's a few other smaller ones, but these are the 2, the ISA 100 and WirelessHART. The ISA 100 committee, it was a group of people, a group of manufacturers, distributors, end users that came together and came up with a series of open standards to produce this, produce that standard. It was designed from the ground up with a defined ISO stack, system management, gateway, and security specifications. I only touched on the security aspect of this system. There's several more security mechanisms built in all the way throughout that OSI stack, from the physical layer all the way to the application layer, that determine, that really lock it down. Highlighting some direct differences, the ISA 100.11a defines and specifies a backbone architecture. That's what we talked about. That minimizes latency, provides added bandwidth and quality of service. I don't have the same potential for data corruption. I can support 1-second update rates. All of those things come along. All of those things that require more reliability and more connectivity come because I'm building out a proper network in the first place. Support for other communication protocols via tunneling. We talked about the NRAF Engage protocol, as well as the GE Bentley Nevada full spectrum vibration analysis or equipment health monitoring. And so that's just the beginning. So there's more and more manufacturers that have these higher bandwidth applications are doing their research and development in order to make them ISA compliant. The field instruments use standard off-the-shelf batteries, meaning Honeywell or Yokogawa or GE or any of the other folks that are on the ISA standard are not in the battery business. You source those batteries locally, you stock them. It's much more cost-effective that way for the end user. Device routing flexibility. I'm saving batteries, and I have a real network if I do not do transmitter routing. If I have a problem that is going to be easily solved or cost-effectively solved by transmitter routing, that's where it comes into play, and that's where I like to use it. So we have that option. The Honeywell OneWireless system combines meshing, radio router diversity, and redundancy features. All of it's built around data availability and reliability. So if I don't want to have to tell an industrial-based customer that the data may be there, it may not be there. It's always going to be there. There's several mechanisms built to ensure that. We talked about adjustable power levels earlier. This is kind of where it comes into play. The out of the box, these transmitters are the radio is at 16 dBm. The WirelessHART radios are fixed at 10 dBm. That is an exponential difference. That is not just 6 dB is about 200% more power output. So I'm getting much more range out of a single device. So that what that kind of equates to is fewer devices. Even though I have a powered infrastructure device, I still have fewer devices as the system grows out to cover a larger space. Flexible provisioning options. Provisioning is kind of what we refer to as security or securing. Every device has to be provisioned before it's going to be allowed onto the network. There's 2 ways to do it in the ISA system, actually 3, but the third one only applies to NRAF. The 2 main ones are through the use of a handheld or a PDA, where the security keys are given or issued by the wireless device manager into the PDA and then distributed by a person through the use of the IR port into every device. That's kind of that's the legacy way to do it. We got some pushback from customers, saying that they didn't necessarily want to buy another device, that that's all it did. So what we did was came up with what's called over-the-air provisioning. And what over-the-air provisioning is it's a feature. You go into the wireless device manager, turn it on, go into the field device access points, and turn it on. So you turn it on in two separate places. That allows the system to listen over the air for ISA wireless devices that are trying to join, that don't have a home already. There is still a human interaction there, because the user or the administrator has to be in front of the interface, see the device come in, and then accept it. So you're still, it's not totally automated. You still have to accept the device. When you see it and accept it through the interface, then it starts that keying process over the air. It's allowed in, and it begins to function. And control rate performance with 1 second device update rates system-wide. Like I said, I can have 100 transmitters at 1 second update rate throughout a system. And the flexibility and performance kind of dictate why the ISA solution is, in my opinion, the best in the market. Why would you select a solution that can only do one thing? And you can easily scale up from a handful of transmitters to hundreds of transmitters while allowing for higher bandwidth protocol via tunneling. Wire-like performance over wireless, thanks to that real network infrastructure that we built out in the first place on the front end. And the instruments support 1 second update rate system-wide while maintaining superior battery life. That's a big deal. The longest transmission range, thanks to radio diversity and higher radio power output. And then finally, we come back to the over-the-air firmware upgrades and configuration. And that all kind of ties together into the flexibility, performance, and ease of use. This is an extremely intuitive system. It's very easy to use. And that was the goal of the ISA standard, is to put something out there that you don't necessarily need engineering services from the manufacturer to deploy, maintain, and upgrade. And that is the end of my presentation.
Brandon, thank you very much for your presentation.
Yes, sir.
There is the ability in the tool, for those in the audience, there is the ability in the webinar tool to ask questions. So if you have any questions while we're wrapping up here, please feel free to type them in and send them through. Additionally, if you have any specific application questions, feel free to give us a call at 800-9-LESMAN or 800-953-7626. If you're not sure who to ask for, just ask for me directly, Mike DeLacluse, and I'll make sure that you get taken care of. Brandon, I'm not having any questions show up, so
okay.
What's that? It is open. I'm not having any questions show up, so at this point, I think we'll conclude the presentation and move on with our days.
Great.
Again, everybody that attended, thank you very much for spending the time. Oh, here comes some questions. With the DuoCast feature, how does that affect battery life?
It doesn't. It's actually, you know what? That's a good question, kind of to talk about redundancy. When a transmitter boots up, it looks for two. It immediately starts looking for a network. It wants to see two devices. If it only sees one, over the long run, and there is no conclusive number I can give you, but over the long run, if there is only one path, that will marginally decrease battery life. It's not a large impact, but it is an impact, because every so often that algorithm is going out and looking for another path. So it wants two paths. So if it forms up both of those paths in the beginning, then that helps your battery life.
All right, I've got another question that came in, but I'm not sure what it is, and it came in from Joseph Martin. I'm going to see if I can unmute him and see if we can get him to ask his question. Joe, if you can hear me, I've just unmuted you, so go ahead and ask your question. It's not coming through. We have another question that came in. Can you explain the full spectrum tunnel?
Yes. Think of it as, I'll kind of use an analogy, and then so I don't have to use technical terms. Think of it as a multi-lane highway, a 5-lane highway. The transmitters are very low throughput, so they're only using about half a lane. I have the rest of this 2.4 gigahertz highway left over. What the engineers tried to do, or the intent, and what they succeeded in doing, was using that available bandwidth for protocols that need all of that room. So, if my transmitters are only using about half a lane, then my GE vibration analysis may use 2 lanes or 3 lanes. So I have this large pipe of bandwidth with a whole lot left over. So what they did is they came up with a way to use that. Now, at more of a technical level, it traverses the network as not as quote-unquote ISA traffic. It's kind of tunneling through the ISA protocol. When it gets to the WDM, it passes it straight through to a specific point. And now I'll use the GE Bentley Nevada solution for that to make that example. When that Bentley Nevada traffic leaves my wireless device manager, it can only go one place, and that's to System 1 software. It is a proprietary, protocol. At the protocol level, it's proprietary, and it's only going to go to that System 1 software to be used, analyzed, and turned into usable data. So while we built this tunnel, we had to be mindful that we didn't create a security hole. So that's how they did that. They created a tunnel that goes through our system straight onto the wire, while at the same time maintaining that high level of security that we built into the system.
Great. The next question, and we need a generality. How does the Honeywell wireless solution compare to Emerson's product package in terms of pricing? Do you know, Brandon?
I know roughly. I don't know it. Obviously, that's going to vary, based on discount levels and things like that. The differentiator is they have 2 devices. They have a base radio that is, the last I heard, somewhere in the $8,000 to $10,000 range, depending on your discount. I'm not. Again, don't hold me to that number. I'm not 100% sure. And then the transmitters. Their transmitters, generally speaking, are a little bit more than ours, maybe a few $100s more than ours. The difference is we implement a 3rd device, or the field device access point. So in that initial installation, we're putting in 3 devices where they would only be putting in 2. The cost effectiveness gets out of whack once you pass that 5 or 6 transmitter level, because at the price difference in the Emerson equipment compared to the Honeywell equipment, even though we have 3 devices, goes away once your system reaches about the 3 to 5 transmitter level. It compensates for the cost of our FDAPs.
Let me tell a little story from one of the applications that we've recently bumped into, and the application was it was underground, which when you apply wireless underground, it's very difficult because your signal tries to go to ground very quickly. And it was in an area that was a couple thousand feet long, so it was very difficult and very tough to make the shots because you don't have line of sight very easily. Our solution worked well because where we couldn't get a signal through, we could install another FDAP and light up another area very easily. The other thing that the customer did that we didn't foresee is they were able to take just an iPad type device down into that area and look up what all the sensors were doing just by getting onto the wireless device manager, which is done through through a browser. So, they were actually able to see their data fairly easily, and it's a very interesting application that is just now being built out, and I think is providing some benefit that that we didn't foresee when they started putting it in, and they just got creative and did some things that we didn't think about initially. So the FDAP really gives us flexibility in lighting up an area with brighter signals and reducing the need to hop through other transmitters, which just reduces a lot reliability by taking the battery life out of them faster. So it's hard, as you just alluded to, it's hard to compare them apples to apples because our implementation is slightly different. But because of that, it gives us some flexibility as we run into difficult spots in the application. So that's just kind of an aside. At this point, I don't have any other questions unless one pops in the last few minutes. Again, if anybody has any applications that they would like to discuss, please give us a call. If you don't know the salesman that calls in your account, please feel free to call me directly. I'll be more than happy to make sure that you get taken care of. At this point, we don't have any further questions, so I think we'll conclude the webinar. Again, thank you for attending. Appreciate you taking time out of your busy schedules. This will be reposted on the website as a recording, so if you want to share it with somebody, we'll have that link out to you shortly. Again, thank you very much.